In this video, we're going to look at two questions on gravity. So, for the first question, it says, assuming the Earth is a homogeneous sphere, calculate the fractional difference between the acceleration due to freefall at the Earth's equator and at the poles, indicating which is the greater. You may not use a value of g given the constants table, so that is 9.81, as that is an average value, neither correct at the poles nor at the equator. And then it gives us the mass of the Earth and the radius. Okay. So essentially what the question wants us to calculate is the fractional difference between the gravitational acceleration at different positions on Earth. And so the major difference between at the equator and at the poles is that at the equator, an object placed there will be at the state of a circular motion. So let me draw a diagram to elucidate this. This is Earth, and let's say Earth is spinning around this axis. So let's say, this object will be at the equator, this object will be at the pole. Now, both of these objects will experience the force of gravity. However, for the object at the equator, as the Earth is spinning, this object will spin with the Earth as well. So it will go like this. And as a result, it will also experience a centripetal force, which opposes the force of gravity. And so essentially the gravitational acceleration will be smaller. And so what we can do is that we can first resolve for GP. GP is like the state where there is no spinning or such. So the easiest way for us to calculate GE, E for equator, would be subtract the centripetal acceleration from the GP. Okay, so first of all, let's say we need to use the formula for gravitational force, which is Fg is equal to gm1 m2 over r squared. Now, because force is equal to ma, so in order to calculate acceleration, we need to divide the force by the mass. Now, in this case, the acceleration is the acceleration of the object, and so we divide it by the mass of the object, and the mass left, the other mass, will be mass of the Earth over r squared. And so now we know me, we know g, it's a constant, and we know r, so we can plug in the values and then resolve for it. Now the gravitational constant that is given is 6.67 times 10 to the power of negative 11 times me, which is given, it is 5.98 times 10. I think there's a typo over here, so that is 10 to the power of 24, I believe, over r squared, so that is 6.38 squared times 10 to the power of 12. Now, all we need to do is plug this into a calculator. So 6.67 times 10 to the power of negative 11, and then times 5.98 times 10 to the power of 24 over r squared, and times 10 to the power of 12, and that will give us 9.799 meters per second squared. Okay, so this is GP. Now we need to calculate GE. Now before that, what I want to do first is calculate the centripetal force, then the centripetal acceleration, and so that we can directly just implement the subtraction. So let's see, G, let's say AC, C for centripetal acceleration, and the formula that I'm going to use is this formula for where it involves the period, so that we can directly just plug like 1 day 24 hours for the period without the requirement to calculate the velocity of the object. And so now we have to resolve for this value. Now 4 pi is a constant, we don't need to know that. Now for t is just 1 day, so that's 24 hours times 60 squared to give us seconds. And then times r is given, it's 6.38 times 10 to the power of 6. And this will give us, let's see, 4 pi is over here, squared times 6.38 times 10 to the power of 6 over 24 times 60 squared, and that will be 0.0337 ms minus 2. Okay, now I will leave the calculator right over here, and because we need to do a subtraction right afterwards. So now in order to calculate GE, we have to subtract the centripetal acceleration from GP, and this will be equal to 9.799 minus 0.0337, which is, see, we can just directly input it over here, 9.799 minus, and that will be, round to 3 decimal places, 9.765 meters per second squared. Okay. Now what we need to do is to calculate the fractional difference. So in order to do this, we have to subtract them first. GP minus GE over GP for the percentage. Okay, so now it will be 9.799 minus 9.765 over 9.799, and this will be equal to, so 9.799 minus 9.768 over 9.799, and that will give us this, so approximately 0.003, and that will be the fractional difference, which is the answer for this question. And apart from that, it says indicating which is greater, so we can say therefore so GP is greater, therefore the gravitational acceleration at the poles is greater. And this will be the full answer to the question. Okay, now for the second question, it says 2 spheres of uniform density, one of mass m1 and radius r1, and the other of mass m2 and radius r2, attract each other gravitationally. what is their relative velocity at the instant of collision if they are released from rest when a great distance apart? Okay. So let's see what we can get from here. So first of all, uniform density. Uniform density essentially means that the mass is uniformly distributed within the two spheres. So this means that their center of mass is at their centroid. And in this case, we can actually establish the conservation of momentum. This is because this is actually a closed system, even though there is a force of gravity that attracts the two spheres together. However, we know from the Newton's third law, each action have an equal and opposite reaction. So essentially, the gravitational attractions will cancel each other out, leaving virtually no forces or net force of zero. And so we can actually establish conservation of momentum. Let me write this down first. Conservation of momentum. And apart from that, I think we can also establish the conservation of energy. What you can say about this is that their initial gravitational potential energy when they're a great distance apart is equal to the final kinetic energy. It's because we can assume that of the gravitational potential energy is transferred into kinetic energy at the instant of the collision. So let's say C, conservation of energy. And let's see, let's draw a diagram first. So this is the smaller mass, let's say M1, and this is M2. So first of all, what we know is that they will be attracted to each other. And so for the conservation of momentum, we have to know their mass and velocity. We know their mass, but we don't actually know their velocity because initially their momentum are zero. Okay, so I don't think we will be able to establish the momentum conservation first. Maybe we can work with the conservation of energy first. Okay. And so what we know is that the gravitational potential energy is equal to, let's say EP, P for potential, is equal to Gm1 M2 over R. This is the equation for it, and there's also a negative sign. And let's say Ek for kinetic is equal to a half mv squared. Now, okay, so, okay, there's one concept I might need to make very clear is that the initial energy is no. So this is actually the initial gravitational potential energy. This is because when these masses are being attracted closer and closer together to a certain point over here, they will lose gravitational potential energy. So essentially what this equation tells us is the gravitational potential energy at an instant that is lost. So that's why it's a negative sign. And so in this case, what we can establish is that the value within it without the negative sign, because this is the gravitational potential energy that is lost, is equal to the kinetic energy that is gained, and we have to consider both of them. So, oh my god, what happened? Oh, I turned this on. Okay. And so we consider the kinetic energy of both masses, because it's possible that the kinetic energy doubled and such. Okay, so plus a half m2 v2 squared, v1 and v2 for the final velocity of the two masses. And what we need to do right now is, okay, let's see what we can do. We can't actually do anything right now. Yes, because it's two variables. And maybe right now we can, oh yes, we can utilize the conservation of momentum. So how do we do this? Let's say m1 v1 is equal to m2 v2. Why? Because essentially this equation is derived from this. So the initial total momentum is 0. And what happens is that they will obviously, the m1 will gain momentum and m2 will gain momentum as well. However, m2's velocity is opposite to m1's velocity. So now this we assume that v1 is the positive direction, so therefore v2 will be the negative direction. And then from this equation we get this equation, okay? And then we can resolve for it. Let's resolve for v1, okay? So v1 in this case will be equal to m2 over m1 times v2. And we can plug this into the previous equation. So g m1 m2 over r is equal to a half m1 v1 squared plus a half m2. Oh, we have to substitute v1. I missed that over here. Let's say this is v2 and m1 and this squared, which is okay. Now we simplify this and then resolve for v2. And then we can factorize it out. So let's switch sides. Factor out. And what is factorized out would be a half. We can actually factorize a half out as well. And what's left inside will be m2 plus m2 squared over m1. Yes. Is equal to g m1 m2 over r. Okay, then we divide it to the other side. Maybe we can simplify the fraction beneath this. This kind of feels weird. So we can time the top and bottom by m1. Yes. Time top and bottom by m1. And we will be able to factorize m2 out from the inside. and what's left is m1 plus m2. And okay, we can also cancel the m2's out, and then we times 2 the other side. So this is r m1 plus m2, and then we got v2. So v2 is equal to the square root of this entire thing. And however, the question wants us to find their relative speed. And so what we need to do is that we have to subtract v1 from v2 or vice versa. So how do we do this? And in one way, we can first resolve for v1. Okay, so what is v1? v1 essentially in this case, we know that v1 is equal to m2 over m1 times v2. Okay, so this is rather complex, but I think we can jump to the next step directly. So v relative will be equal to v2 minus v1, which is equal to, because we can factorize this entire thing out, and so let's write this down first. And what happens is, when we factor this entire thing out, is this 1 minus m2 over m1, right? And so we can further simplify this. And what we can write this as is m1. Let's see, so this becomes m1 over m1. This is minus m2 over m1. And I think I made a small mistake, I believe so. Or maybe I've overthinked. Because I think it might be a positive sign instead of a negative sign. But anyways, let's resolve for this first. indeed. I made a simple mistake. Okay, so let me explain this. So over here, V2, I essentially assume that V2 is essentially what I did is I factorized a negative sign out of V2 because this is supposed to be a positive sign instead. And I factored the negative sign out of V2. So in this case, what actually need to be written is this negative V2 minus V1. And maybe there's an easy way of doing this. We can just do it the other way. So the other way around will be V1 plus V2. Okay, now this makes sense. And this will be the plus sign. Okay, let's proceed. And so what happens right now is that this thing becomes m1 plus m2 over m1, and we can essentially write this as m1 plus m2 squared over m1 squared. And then we can see that this cancels out, this cancels out, this one and this one cancels out. What's left would be 2g m1 plus m2 over r. Now, one thing that I realized is that I didn't resolve for r, but it's quite simple. So r is essentially the distance between the two spheres during at the instant of collision. That would be r2 plus r1 because the two spheres is very close to each other, and so the distance between their two center of mass will be the sum of their radius. And so the final answer will be this. And this will be the answer for this question.